Okay.
Yeah. Oh, right.
Okay, so thanks for inviting me. And I'm going to talk about Hochschild homology. And I'm going to talk about certain computations of Hochschild homology. So let me, I think this is the name of my talk. I'll be talking about Hochschild homology, but the same things that I have to say hold for Hochschild cohomology. Okay, but the important part of the talk are these homotopy epimorphisms. Okay, so let me motivate. Okay, so let's take the case of a commutative ring. Then what we know, say through the proof of what is called the Hochschild-Rosenberg theorem, an intermediary step in that proof is to show that the Hochschild homology of a commutative ring, it doesn't matter over what field or ring you're working over. So the Hochschild homology, this is defined as, say, the bar resolution. And you base change it, or you take its commutators with A, so you can treat this as a definition. Now, this is a model for the derived tensor product. So the derived tensor product literally just means whatever I've written here. And in particular, you can choose any projective resolution. Okay, so as I was saying, in this, in many different types of proofs, including that of the Hochschild-Rosenberg theorem, what you want to show is that if you take, say, if you base change Hochschild homology with the localization of a commutative ring at some element, then this is the same thing as the Hochschild homology of the localization. And in a sense, what you're using is that localization commutes with tensor products. Okay, and this is used to show what is called Zariski descent for schemes. And this statement is just that Hochschild homology satisfies Zariski descent. And this is used to reduce the computation for, say, smooth algebras to either étale algebras or even polynomial algebras. Okay, so a question that you might ask now is, what if you work over in, say, the category of simplicial commutative algebras, which, now why would you want to do that? It's because that is the category in which derived geometry is built. So if you have what is called a derived localization, which I'll come to in a bit, then is the same thing still true? That is HH of B the same thing as HH of A, derived tensor product over A with B? Okay, so that is one question you might want to ask. Oops, that I did not mean to do. Okay. Okay, then the second motivation is something that comes from analytic geometry. So this is a motivation which comes from derived geometry. This is a motivation which comes from analytic geometry. And this goes as follows. So if you have, say, a smooth commutative algebra, so if you don't know what that means, say this is a polynomial algebra. Whatever I have to say essentially boils down to computations for polynomial algebras, which we do understand pretty well. Okay. Now in analytic geometry, as the name suggests, you want to take something that is just an algebra and you want to spike it with a topology. So what you can do is you can take the analytification of the algebra. Let me also put this in quotations because at the moment we don't know what it means. Okay, now analytifications, because you're adding a topology to some algebra, it makes it all the more complicated. But again, as in the question above, what you might want to ask is the Hochschild homology of the analytification in some sense the same thing as the Hochschild homology of the algebra derived tensored over the algebra with the analytification? So what that would say is that you have this algebra A, which you understand very well because it is, say, the polynomials and invariables, and you have the relations between Hochschild homology and differential forms, so you do understand it well. On the other hand, you have this gadget A_n, which you do not understand very well. But for the same reasons that Hochschild homology is important in, say, deformation theory, the analytification of the algebra is perhaps something that plays the same role in analytic deformation theory. So you might ask the same question again. What is its Hochschild homology? And this is a speculation that you might arrive at. Okay, now before I move forward, let me give some examples of analytification just so that you have something in mind. Okay, there's a whole bunch of different types of analytifications that are possible. Let me give a few. So let's take the case of the p-adic integers. Let's say you're working over a field K or a ring K. Then an analytification of, say, the polynomial rings is, well, let's take the Tate analytification. This is given by convergent power series. So this is just a collection of power series such that the norm of this converges to 0. And this is just the p-adic norm. You might also take the same thing if you don't know what the p-adic integers are. You can take the complex numbers. And then you can take the same kind of completion again. You can take the formal power series that are in some sense restricted. So this is a restricted formal power series. Such that the supremum of these is finite. Okay, so these are some examples of analytifications. You go from polynomials and you take some power series with some conditions on the coefficients. Okay. A third motivation goes as follows. Now let's forget about commutative algebras. Let's take non-commutative algebras. So say A is a non-commutative algebra. Again, over any field or ring, whatever, that doesn't really matter. What often happens is you might say want to compute the periodic cyclic homology or some other variant of cyclic homology, which are derived from Hochschild homology. But that is something which is in general not computable, unless you can say something about its Hochschild homology. So the right generalization of derived homology in the non-commutative setting is, let's say, periodic cyclic homology. But periodic cyclic homology is, again, only computable for smooth algebras. So you might now take the case where, well, you might take some smooth subalgebra of this non-commutative algebra, say I denote it by A infinity. Let's say we take a smooth subalgebra and try to understand the periodic cyclic homology of A infinity. But again, that's not the algebra we want to understand. We want to understand the periodic cyclic homology or some invariant of A itself. But okay, this is at least some starting point where we might have some hope of answering questions about the algebra A itself. Okay, but a priori, there's no reason to expect that the periodic cyclic homology or any invariant of A infinity is any easier to compute than A. So what you might then do is take something which is polynomial type and these polynomial type algebras are things where you might be able to compute their Hochschild homology. Okay, so now this is all pretty abstract. So let's take some examples. Let's say we want to understand the group algebra, the L1 group algebra of some discrete group G. Say Z. So that is a A. Now, if you know something about cyclic homology, then this is something which is practically impossible to compute. So instead, you take what is called the Schwarz algebra of G. So these are let's say, power series, with rapidly decreasing coefficients. Okay, so you might have some hope of understanding this smooth algebra, but not really. You only understand it because you understand the group algebra, the honest group algebra, which is sitting inside A infinity. So this is a polynomial. And this is something where you can say a lot. This is just the group ring over the complex numbers. You can compute its Hochschild homology, you can compute its periodic cyclic homology. And it's related to the group cohomology of the group. Okay, but again, as in my previous two questions, you might again ask, what is the relationship between the Hochschild homology of this group algebra and the Hochschild homology of the Schwarz algebra, or in general, the Hochschild homology of some polynomial type algebra and the Hochschild homology of some smooth subalgebra of a given noncommutative algebra. Okay, so these are kind of three classes of algebras I want to say something about. Okay, and the answer is that, oops, okay. The answer is that you can answer all these questions because these three embeddings are of a very specific nature. These embeddings, in the first case, it was the localization. And in the second case, it was the analytification. And in the third case, it was some polynomial type algebra inside some smooth algebra are examples of the title of my talk, which is Homotopy epimorphisms. Okay, and now let me define what homotopy epimorphisms are. So let A and B be, let's say, algebras in some symmetric monoidal category. And F some morphism. Then we call F homotopy epimorphism. If it satisfies the following, which I'm going to explain in a bit. If you take the derived tensor product of B over A, then this is the same thing as B. Okay, now let me explain what that means and why it has anything to do with Hochschild homology. Okay, are there any questions until this point? Okay. Okay, so where does this mysterious thing come from? Let's see. Okay, so how do we compute the Hochschild homology of any algebra? As I pointed out, to compute HH, what we need is a projective bimodule resolution. So let's say we're computing the Hochschild homology of A, need a projective A bimodule resolution. Okay, now, as I said, this might be impossible to do. Often when we want a projective resolution, we might want a short projective resolution. Otherwise, you don't get any information out of what you set out to compute. So the question is, what is a projective resolution of B given some algebra homomorphism F from A to B? You might do a trick, which is you might just base change and if you do this base change, then, well, the A's cancel out, so you just get B. Okay, now the problem by doing this base change, or the problem with this base change, is that this is not necessarily a resolution. This is... And well, why is it not a resolution? It's because tensoring on both sides with B is not a functor. It's not an exact functor in particular. But it turns out that if F is a homotopy epimorphism, then this is a resolution. Well, I should not put an exclamation mark before a lemma, but okay, you get the excitement. Okay, and the good part is that this is an if and only if statement. So this is a resolution if and only if F is a homotopy epimorphism. So that mysterious derived tensor product condition simply boils down to this more concrete statement. And well, this is equivalent to another abstract statement. That is, if you take the derived category of B modules, then that embeds fully faithfully inside the derived category of A modules. Okay, so this is, again, this is just a conceptual explanation, but it's not something you can compute in practice. This is the only thing that you can actually do in practice. You might be able to check whether this is a resolution if you have a good reason to believe it is. Okay.
Excuse me, can I ask a question?
Mm-hmm.
Is it possible to see that as like a tensor over the enveloping algebra with the enveloping algebra of B, or
Yeah.
maybe is this a different thing?
No, it's the same thing. Yeah.
Ah.
That is how you prove this sort of a statement. Yeah.
That is why you need it to be a symmetric category.
Yeah.
Ah.
Yeah. Precisely.
I feel more comfortable with things only on one side.
Yeah. Well,
Thank you.
right. Okay. Right. So now let me say what I mean by projective in this context. Because as you can see, we are working with things which are not just algebras, they're algebras with topology. So saying that something is a direct summand of a free module makes no sense in this context. So this is why one works in this more abstract setting. You start with a symmetric monoidal category and you define things relative to some exact structure on a symmetric monoidal category. Okay, so that takes me to the second part of this talk, which is homological algebra.
Excuse me, another question. Sorry.
Mhm.
When you say that you want to put topology in the setting, you may put topology in the category C, or
Well, the category C already has, we are working in the category of topological modules, but a specific kind of topological modules. In particular, it's not very literally the category of topological modules. You have to specify what kind of topology you want. You want the category to be as close to abelian categories as possible. And the category of topological modules, depending on how you define them, need not exhibit that behavior. Okay, so that is exactly this part of the talk, which is how do you do homological algebra when your modules come with topologies? Okay. Right, so one possible option for your category C could be the category of Banach spaces. This is a reasonable category of topological modules or topological vector spaces. Let's say we work relative to Banach spaces over R, where R is either the complex numbers or even the real numbers or QP. It doesn't really matter. You can even take fancier things, but basically any what is called a Banach ring. Okay, but sadly, this category is not complete and co-complete. It is only finitely complete and finitely co-complete. Okay, so clearly you need to enlarge the category. You have two possibilities for enlarging the category. One is you take the category of formal inductive systems called ind Banach spaces. Or you can take the category of pro-Banach spaces. So these are the categories of functors from I to Banach spaces over R, such that I is a directed set. Or you can take the pro-completion, but the category I prefer to work in is the category of inductive systems of Banach spaces. And why do I prefer to do that? It's because it is also a closed symmetric monoidal category. And what do I mean by that? So let me state this as a lemma. C is, well, first of all, it has all limits and co-limits, just like projective systems of Banach spaces. So this is bi-complete. Secondly, C has enough projectives. Furthermore, there is a tensor Hom adjunction. Okay, let me put this in quotations. Where the tensor is given by the completed tensor product. This was originally defined by Grothendieck. The completed tensor product is something which exactly mimics the algebraic tensor product. That is, you have a universal property between linear maps out of the tensor product into bounded bilinear maps. Apologies for this notation. Okay. So this is exactly like the algebraic tensor product, which would just be A tensor B to C. So linear maps from the tensor product of two vector spaces are the same as bilinear maps, that is without the word bounded, from A times B to C. Okay, so that is what the tensor product is. And right, this turns it into what is called a closed symmetric monoidal category. Okay. Right, so this is still just algebra. We still don't have any kind of homological algebra, and that's why I put the projectives in quotation. The thing is, C is very close to being an abelian category, where all these objects are defined. That is, what is a projective, what is a free object. C is a quasi-abelian category. And what is a quasi-abelian category? If you take the co-kernel of any morphism, then if you take the pullback of a co-kernel, then first of all, it exists. And furthermore, it remains a co-kernel. So co-kernels are stable under pullbacks. And furthermore, kernels, or dually, kernels are stable under pushouts. Again, in particular, if you don't care about what abelian, quasi-abelian categories are, then what is true is that any quasi-abelian category embeds fully faithfully inside an abelian category. Okay, so the category we are working under, or this huge category that I just described, of inductive systems of Banach spaces, is a quasi-abelian category. Great. And now in a quasi-abelian category, we can define projectives as follows. Projective objects. So you say P is projective if the home functor from the category C into the category of abelian groups is, or preserves co-occurrence. So it's just the same as the usual abelian category definition of projectives, except you replace surjections by co-kernels. Okay, but we want to define projective objects relative to some algebra. That is, we want a projective bimodule resolution relative to the algebra whose Hochschild homology we care about. So what we do is, we do what is called relative homological algebra. Now, since this is a symmetric monoidal category, we can define algebras in it. So let A be some algebra inside this category. We can then define the category of modules relative to that algebra. And this is still quasi-abelian. And of course, it is symmetric, monoidal, and so on. With respect to the completed projective tensor product over A. And you say a module P is projective if, again, this condition holds. Okay, so that's what a projective module is. You might ask, what is a free module? Because those are the objects which are easier to deal with. So a free A module over some, let's say, V inside C is one of the form A completed projective tensor product with V. So these are the free modules. And to convince yourself that these really are free modules, what you need to check is that it satisfies the universal property. That is, if you take maps out of this into some X, then this is the same thing as maps from V to X, which is exactly the usual notion of free modules if you work, say, over the category of modules. You have the free forgetful adjunction, in other words. Okay. Right, so now that we have the basic homological algebra set up in quasi-abelian categories, let's now get back to the original problem, which was these homotopy epimorphisms. So, analytifications, localizations as homotopy epimorphisms. I'll get back to the non-commutative one after these. These ones are particularly simple. Okay, so the theorem is that A to AN, where recall that A was something that was polynomials and AN was power series with some convergence conditions on the coefficients. So this is a homotopy epimorphism. And the proof, or the sketch of the proof, is as follows. First, we do it for polynomials. So A is, let's say, we're working over some ring R, some Banach ring R. And let's actually do it for polynomials in one variable. Now, for polynomials in one variable, you know you always have the Kosul resolution, which is just the, well, it's just A tensor A with A tensor A, and then the diagonal map to 0. So this is just the Kosul resolution. So this is a free resolution of R of X. Okay, now we analytify the Kosul resolution. This is something one checks by hand. It turns out that the analytification, whatever analytification you choose, is still a resolution. And this is something that we check by hand. And the same maps as in the Kosul resolution worked in this case as well. So this is a free resolution. But of the analytification. Now, the whole reason why I mentioned all this about relative homological algebra is that the freeness comes for free, because this is just R of X, tensored over R, analytified. Over this. And these were precisely the free bimodules. Okay. So this would imply that okay. Right. So what that does is it computes a very short projective resolution of the analytification of the polynomial ring in one variable. And this, as we mentioned, was a model for the derived tensor product. So what this implies is that R of X and derived tensor Well, actually don't need to mention this because of the equivalent criterion I gave. That is, when I start with a projective resolution of R of X and I tensor on both sides with the analytification, then this resulting thing is a resolution. So this says that R of X to R of X and is a homotopy epimorphism. Okay, and then what we do is by abstract nonsense. So, oops. So by properties of these epimorphisms, if you tensor a homotopy epimorphism with a homotopy epimorphism, then the resulting thing is still a homotopy epimorphism. And if you do that n times, what you get is that the polynomials in n variables to its analytification is a homotopy epimorphism. Okay, so that's the analytification of the affine plane. And the rest again goes through by abstract nonsense. What we now have is polynomials over R, so polynomial algebras over R, inside the category of simplicial commutative algebras over R inside our category C. And what this is nothing but the analytification. And then what we do is take the left Kahn extension to all simplicial commutative algebras over R. So this is just the left Kahn extension of the analytification functor. So you apply this to any simplicial commutative algebra, in particular, any commutative algebra. And this would be the sifted colimit of the individual analytifications of some free resolution of A, where P is a simplicial resolution. Okay, but the point is, if you can do it for polynomials, you can do it for any commutative algebra. Okay, but that's not yet a statement. The statement is that an intermediary lemma would be to say that sifted colimits of homotopy epimorphisms is a homotopy epimorphism. Okay, and that would imply the theorem, because we proved it for polynomial algebras. Okay, well. Okay, so that's the proof for analytifications. The proof for localizations is, again, very similar. You prove it for polynomial rings. And then you, again, need to prove a lemma about derived push-outs being closed under homotopy epimorphisms. So localizations or derived localizations are homotopy epimorphisms. So the proof would be, if you have a map from A to B, which is, so if this is a homotopy epi, and you take an arbitrary map out of C, out of A, then if you take the derived push out, then this is a homotopy epimorphism. And if you take some concrete cases, such as, well, I mean, this applies to, in particular, the derived quotient. And that proves it for the derived localizations we consider. So do this for derived quotients. Which is a special case of this derived push out. To get the result for localizations. Okay, and the point is that localizations are a complicated business outside of algebraic geometry. In algebraic geometry, it's just inverting certain polynomials. But in analytic geometry, there are many different types of localizations. But this general argument gives it for all sorts of localizations. Okay. Right. So that's that shows that localizations and analytifications are both homotopy epimorphisms. So we can reduce the Hochschild homology computation for these complicated algebras to simpler algebras, which we can always say something about. Okay, now the final thing is the non-commutative case. Okay, so in this, the result that I have is more partial because it's somewhat more complicated in a very different direction. So here the result is for a very specific analytification, which is called the overconvergent analytification, which is useful if you want to do cyclic homology in the non-Archimedean or the p-adic setting. So for smoothing of a specific kind. Okay, so the result is as follows. So let A be non-commutative ZP algebra. And let's say it does not have P torsion. Then A to Let me denote this by a dagger because that's how I denote such algebras. But morally, if A is commutative, or rather in the commutative case, A is polynomials in n variables or some quotients of polynomials. So this was the A poly notation. And A dagger would be the A infinity in that notation. So the smoothing of an algebra. And what we want to comment on is the Tate analytification, which I at some point of time in the start pointed out. And this would just be the p-adic completion of the algebra. So this is the thing that we want to say something about. And in general, there's no reason to expect good behavior for this. So we take this smooth algebra. And the only thing that we can say something concretely about are these polynomial algebras. And there is also this is the non-commutative generalization of that fact. Okay, so the point is that this is a homotopy epimorphism. And the proof of this goes as follows. Okay, so let's start with some projective resolution of A. The only one we generally know for any non-commutative algebra is the bar resolution. So take the bar resolution of A. This is a free A bimodule resolution. Okay, now if we tensor on both sides with a dagger, then this is, by completely different reasons, a resolution of a dagger. It's a typo. And the reason is that A to A dagger is flat algebraically. And because it's algebraically flat, I've used the incomplete tensor product over here. But then by a functional analytic argument, which is the closed graph theorem, this thing is the same thing as the completed tensor product. And this continues to remain the resolution. But this time that's where the closed graph theorem comes in. It's a resolution in the right category. In set P. Okay, and that would conclude the proof that A to A dagger is a homotopy epi. Okay, and just to summarize, if A to B is a homotopy epi, then what we have is the Hochschild homology of B is the same thing as the Hochschild homology of A derived tensor over A with B. And this applies to all the three cases that I mentioned. And yeah, just the summary is that this is computable. So in that sense, HH of B is computable. Okay, that's all I have to say.
Wow, thank you, Dev. Right.
You guys have questions?
So, do you have some examples for family of algebras? Or?
Well, so the examples are exactly the ones I motivated, right? So the one part of examples come from analytic geometry. You take some, let's say, a scheme, and then you take the analytification of the scheme. So you view it as a complex variety, let's say. Then you can compute the Hochschild homology of the complex variety in terms of the Hochschild homology of the underlying variety without the
Yeah, because in general it's really difficult, but maybe that examples are the usual examples. So maybe other examples.
You can, for instance, do this for you take the group algebra, and you can take its say the noncommutative torus. So this technique was used by Alan Kohn to compute the cyclic homology of the noncommutative torus. So that's another example which fits in this scheme of things. And what else could fit? Yeah, basically any kind of localization fits into this, any kind of analytification fits into this, and the non-commutative analogs of analytifications also fit into this.
Okay, thank you.
Don't have any more questions? I have one, but is just because I don't know much. That derived tensor product is also an easy thing to compute, or I've never seen that.
Well, so the derived tensor product is actually just fancy notation for what you always do when you compute the Hochschild homology of an algebra. Say with what? Yeah, so how do you normally define this? You take some projective resolution of the algebra and you base change it. Let's even take the non-commutative algebra A. And you tensor it with A. This is just by definition the same thing as the derived tensor product of this. So derived tensor product is the tensor product in the derived category of modules. And the derived category of modules, the objects in that are chain complexes. So in the derived category, there's no difference between a module and its resolution. So you just take the resolution and you take the tensor product either term-wise, or you just view it as an object in the derived category and take the derived tensor product. It's the same thing.
You take the total complex and that's it.
Yeah, I mean it's not even total complex. It's just a point-wise tensor product.
Okay.
So for instance, if you took the bar resolution of an algebra, this is given by this. So the derived tensor product of A, let's take commutative so that I don't need to write op. The derived tensor product of A over itself, this is just by definition the chain complex. And then you tensor over A. This should be an A tensor A. So it's just this chain complex.
Okay. I was thinking you put chain complexes in both sides, but
that's equivalent. Yeah. So you can also resolve A from the other side, because in the derived category, there's no difference between A and a resolution of A. So yeah, you can also do that, but these are all up to quasi-isomorphism, the same object. And quasi-isomorphisms are isomorphisms in the derived category.
Great. Thank you. It's really nice. Last chance for a question. We already asked a lot. Well, thank you again, Dev. Thank you for accepting.
No worries. I can give it up whenever.
Okay. Next year, maybe you can talk about what you're doing right now.
Sure. Yeah, I could do that.
Right. People come to the seminar and they want to come again and again.
Yeah, I mean, do you guys have a mailing list or something, or?
Yes, I was about to ask you if
Because
you...
the email didn't come through the Comunidad email address in the DM, so maybe if you guys send it on the community email, then I would also receive those emails.
Yes, Christian is in charge of the... Maybe Christian, you add his address to the list, and great. So you can, for example, you can come next week and see Anna's talk.
Sure.
Yeah.
Great.
Great. Thanks a lot for inviting me, and see you guys next time or next year.
Or next week.
Yeah, next week. Yeah. The problem is that at the same time, I organize the infinity category seminar.
Wow.
So that's what creates this clash. But yeah, we'll look into that later.
Okay. Thank you.
Thanks a lot.
See
You can
Bye.
see it in YouTube, some of the talks also,
Mhm.
if you're interested.
Great. Bye.
Bye.
Thank you so much.